We are going to start now the next lecture, lecture 5 of class 12th mathematics, chapter 1, relations and functions. Now in this lecture we will talk about the invertible functions. So suppose we have a function f that is defined from a to b, and if there exists another function g that is defined from b to a such that GOF is equal to IA and FOG is equal to IB, then f is called invertible function and g is called the inverse of f, and it is written like f inverse of g. I am again repeating the definition. We are saying f is a function defined from a to b. This function is called invertible if there exists a function g defined from b to a such that GOF is equal to the identity function and FOG is equal to the identity function in B. Then this function f is called invertible and g is called the inverse of f, and this g can also be written as f inverse. So we have explained this thing with an example over here. So suppose a function f is given, it is defined from R to R, and the definition of the function it is fx is equal to 2x plus 3. Now suppose we write y is equal to fx, that is equal to 2x plus 3. So this thing implies us that x is equal to y minus 3 by 2, and this is say the function g of y. We are saying this is basically the inverse function of over here, or we can write it is f inverse of x, that is equal to x minus 3 over 2. How we are saying this thing? We are saying because if we calculate GOF of x, the answer we have it is g of fx. Now what is fx? It is 2x plus 3, so it is g of 2x plus 3. So we are saying this is equal to 2x plus 3 minus 3 by 2, and the answer we obtain it is equal to x. So what we get from this is that GOF of x is equal to x. It means GOF is equal to identity function in R. Similarly, we can prove that FOG is an identity function in R. So we are saying this function g we have obtained over here, g of y we are talking about, or we are writing it is f inverse of x. This function is the inverse function of the given function f. The next theorem that we have to prove it is if f from a to b is 1 1 on 2, this function it is given to be it is 1 1 as well as on 2. We have to prove that the function f is an invertible function. So as it is given that this function f from a to b it is 1 1 and on 2. So we are saying let there be an element y which belongs to b, then f being 1 1 on 2, there exists a unique element x belongs to a. This term unique comes because it is 1 1, and the existence of this element is because it is on 2, and it is such that f of x is equal to y. Now we are defining the function, there exists a function from b to a such that g of y is equal to x. What we mean to say, suppose we are saying we have two sets over here, one is set A and one is set B. Suppose we have three elements over here, 1 2 and 3, and we have three elements over here, it is A, B and C, and the function that is defined over here it is 1 is mapped to B, 2 is mapped to A and 3 is mapped to C, because the function is 1 1 as well as on 2. So on 2 gives us that in this set B there is no element for which the pre-image does not exist, and 1 1 gives us that each element over here A, B and C, it has a unique pre-image, and this is the function f we are talking about. Now we are saying there exists a function g from B to A, and it is defined like g of y is equal to x. So when we are talking about the function f, we are saying f of 1 is equal to B, f of 2 is equal to A, and f of 3 is equal to C. And when we are talking about the function g, we are saying the function g is g of A is equal to 2. Now this A is mapped to 2. G of B is equal to 1 and G of C is equal to 3. We are talking about this function over here, that there exists a function g from B to A such that g of y is equal to x. Why this is a function? Because we have already seen over here that this x belongs to A is unique. Now when we are talking about this term GOF of x, we have to show that we are saying that the function f is invertible. First thing we have to prove over here is that there exists a function g such that GOF is equal to identity function in A and FOG is equal to identity function in B. We have to prove this thing. To prove this, we have already shown that there exists a function g from B to A. Now we are talking about the value of GOF of x, and we have this is equal to g of f of x, and this is equal to, what is f of x? F of x is equal to y. It means we are getting it is equal to g of y, and g of y is equal to x. So what we get is that GOF of x is equal to x. So this thing implies us that GOF is equal to identity function in A. Similarly, when we are calculating GOF of y, we are writing it is f of gy, and we obtain that this is equal to identity function in B. So what we have obtained is that there exists a function g such that GOF is equal to identity function in A and FOG is identity function in B. So we obtain that f is invertible and f inverse is equal to g. Now the next result written over here, it is if g is inverse of f, then the graph of g is the mirror image of f, and the graph of f is the mirror image of g. This thing is shown over here, that if the graph of this function y is equal to x square is this, then we have considered a line over here y is equal to x, and the image of this line y is equal to x square, it is this and this is the graph of the function y is equal to square root x. So we are saying these two are the mirror images along the line y is equal to x. So this thing is, I am again explaining over here, that if g is the inverse of f, then the graph of f and g are the mirror images of each other. Now the next theorem we have is, if f from A to B is a function and it is given that it is an invertible function, then we have to prove that f is 1 1 and onto. So if f from A to B is an invertible function, it means there exists a function g from B to A such that GOF is equal to identity function in A and FOG is an identity function in B. Now we have to prove that it is both 1 1 and this f is both 1 1 and onto. So to prove that it is 1 1, we are considering, suppose there are x1 and x2, there are element x1 and x2, they belongs to A, and f of x1 is equal to f of x2. So this thing will imply us that g of f of x1, that will be equal to g of f of x2, and this thing will implies us, what is this g of f of x1? It means we are talking about g o f of x1 is equal to g o f of x2, and g o f, this is identity function in A, this is identity function in A, and this thing implies us that x1 is equal to x2. So we are saying if f of x1 is equal to f of x2, this thing implies us that x1 is equal to x2, and hence we obtain that the function f is 1 function. Next we have to prove is that f is an onto function. So suppose we are considering an element, say y belongs to B, then we have g of y, it belongs to A, because there exists a function g from B to A. So g of y, that will belong to A, and this g of y means we are considering, suppose this g of y that belongs to A, that is equal to some element x. Then what we have is, then we have g of y is equal to x. This thing implies us f of g of y, that is equal to f of x. Now what is this term? This term is f o g of y. So this thing implies us y is equal to f of x. So what we get is that for every y belongs to B, we have some x that belongs to A, such that y is equal to f of x. So it means that for each y belongs to V, there exists x belongs to x such that y is equal to f of x, and this thing gives us that f is onto function. So combining these results, we obtain that if a given function is invertible function, then that function is both 1 and onto. Now the next question we have is, let f be a function defined from R to R, and the definition of that function is fx is equal to 4x plus 3 for all x belongs to R. We have to show that f is invertible, and we have to find the value of f inverse. So to prove that f is invertible, we are going to prove that this function fx, it is both 1 and onto. So to prove that this function is 1, we are saying let x1 comma x2 belongs to R, then f of x1 is equal to f of x2. This implies 4 of x1 plus 3 is equal to 4 of x2 plus 3, and this implies as x1 is equal to x2. So it means this function is 1. Next we have to prove that this function is onto. So to prove this function is onto, we are writing y is equal to 4x plus 3. So this gives us x is equal to y minus 3 by 4. So this is equal to some function g of y. Now the domain of g, that is equal to R. This function, it is defined for all real number R, and this is equal to range of f, and this is equal to codomain of f. So we are saying this function is onto function. Now as it is both 1 and onto, that is, it is bijective. So what we get is that this function is therefore invertible. That is, we can find the inverse of this function, and the inverse of this function, this we are talking about over here. We are saying we have equated y is equal to 4x plus 3, and we have obtained a function g of y that is equal to y minus 3 by 4, and this is basically the inverse of the function f. So we are saying we have defined the function f inverse from R to R such that f inverse of y is equal to y minus 3 by 4 for all y belongs to Next is let R positive be the set of all positive real numbers. Let f be a function defined from R positive to 4 comma infinity such that fx is equal to x square plus 4. We have to show that f is invertible and we have to find the value of f inverse. So to prove that f is invertible, we are going to prove that the function is both 1 1 and on 2. So we consider x1 comma x2 is belongs to R positive. We are writing f of x1 is equal to f of x2. This implies us that x1 square plus 4 is equal to x2 square plus 4, and this implies us that x1 is equal to x2 because both of these are the positive real numbers. So we get that the function is 1 1 function. Next we have to prove that it is onto. So to prove it is onto, we are going to find the range of this function. So we are equating we are writing y is equal to x square plus 4. So this gives us that x square is equal to 4 minus y, and this gives us x is equal to square root of 4 minus y. We are not considering negative sign over here because this x, it belongs to R positive. Now this function, this value we are talking about, this will exist if we are having y is greater than equal to 4. So this thing implies us that y belongs to interval 4 comma infinity. So this thing gives us that the domain of the function f, that is equal to the interval 4 comma infinity, and this is equal to this is the range of the function. This is not the domain. I think this is the range of the function f, that is equal to 4 comma infinity, that is equal to the co-domain. So this gives us that the function f, it is onto function. So combining both these results, we obtain that the function f is a bijective function and therefore it is invertible, and the inverse of this function, it is given by, look at this condition over here. We are saying this gives us the function f inverse of y is equal to square root of y minus 4, and f inverse, it is defined from the interval 4 comma infinity to R positive. So this function is the inverse of the given function f. Now in this question, we are given that R positive is the set of the positive real numbers, and it is the function that is defined over here. It is f is defined from R positive to R positive. It is the domain, and the codomain, it is set of positive real numbers, and the function is defined like fx is equal to e raised to the power x. We have to show that the function is invertible. So we are considering x1 comma x2, they belong to R positive. So f of x1 is equal to f of x2. This implies us e of x1 is equal to e of x2, and this implies us x1 is equal to x2. It means this function is 1 1. Next, to calculate the range of this function, we are writing y is equal to e raised to power x. So this gives us x is equal to log of y. So we are saying that this function, this value of x, this will exist for all values of y greater than 0, and this thing implies us that y belongs to R positive. So the range of this function f, that is equal to the interval, or we are saying it is equal to the set of all positive real numbers, and that is equal to the codomain of this function f. Hence this function is also onto. We are having this function is 1 1 as well as onto. It means this function is invertible, and the inverse of this function f inverse, it is defined from R positive to R positive, that is set of real numbers, and it is defined like f inverse of y is equal to log of y for all y belongs to R positive. Now the next question we have is, the set A is given. It is the real numbers between minus pi by 2 to pi by 2. So A is basically the set closed interval minus pi by 2 to pi by 2, and B is the set of all real numbers between minus 1 and 1. We have to show that the function f from A to B, fx is equal to sin x, is invertible, and hence we have to find the f of inverse. Now to prove that this function is invertible, we have to prove that this function is 1 1 and on 2. So if we plot the graph of sin x from the interval minus pi by 2 to pi by 2, we obtain that the graph of this function, it is of this form. This is our y-axis, this is our x-axis. The value over here it is 1, the value over here it is minus 1. So if we draw a line parallel to x-axis, we obtain that it will intersect this graph at only one point. So this function, it is 1 1. Further, the range of this function, it is from minus 1 to 1. It is closed interval over here, and that is equal to the codomain. So this function is also onto. So if you don't want to use the graph, of this function, what you can do is, we are saying, suppose we have x1 and x2 from this set A, then f of x1 is equal to f of x2. This implies us sin of x1 is equal to sin of x2, and this implies us that x1 is equal to x2. So we get that this function f is 1 1. Further, we have seen that the range of this function, it is minus 1 to 1, so it is an onto function. So we obtain that this function sin x, fx is equal to sin x from A to B, this is an invertible function, and the inverse of this function, we write y is equal to sin x, then we obtain x is equal to sin inverse y, that is equal to some g of y, or we are writing it is f inverse of y, where f inverse is the function defined from minus 1 to 1 to minus pi by 2 to pi by 2, and definition of this function f inverse of y, that is equal to sin inverse of y. So this function we are talking about, this is sin inverse of y, and this function we will study in our chapter of inverse trigonometric function. This function, it is called inverse trigonometric function. Now the next question we have is, f is a function defined from n to y, and the definition of the function, it is fx is equal to x square, where y is the range set of f. We have to show that f is invertible, and we have to calculate the value of f inverse. So if we consider two elements x1, x2, they belongs to n, then f of x1 is equal to f of x2. This thing implies us that x1 square is equal to x2 square, and this thing implies us x1 is equal to x2, because both x1 and x2, these are the natural numbers. So we obtain that this function is 1 1. Further, it is given that in this question, it is given that y is equal to range of f. So this thing implies us that the function is the on this function y, it is onto function, and therefore it is bijective function, and bijective function, so this implies us it is invertible. Now we have to calculate the inverse of this function. So we suppose that y is equal to f of x. So this thing implies us y is equal to x square. So this gives us that x is equal to square root of y. Why? Because the domain of this function, it is n. So we are writing that x is always positive. So we obtain a function, yes, in f inverse, that is defined from this set y to n. This y is already there, it is basically the range set of f, and the definition of this function, we are saying that f inverse of y is equal to square root of y. So this is our inverse function corresponding to the function f. Now suppose in this question in place of n, if it is r, then f from r to y we are talking about, then what we will have is that this function fx is equal to x square. This will not be an invertible function because it will not be the 1 function. We are saying it is not 1 function because f of 1 is equal to 1 is equal to f of minus 1. So it is not 1. It means it is not bijective. So this function, it is not bijective, it means this function is not invertible. But when we are considering the domain as n and the range as this set y, where y is equal to range of f, then we are saying that this function, it is invertible, and the inverse function is given by this formula. Now next function that is given to us, it is fx is equal to x over x plus 2, and the domain of this function, it is given from -1 to 1, and the codomain of this function, or codomain of this function, that is y, that is equal to range of f. We have to show that the function f is invertible, and we have to find the value of f inverse. So to prove that this function is invertible, first of all we are proving that this function is 1. So we are considering two elements x1 and x2 that belong to the closed interval -1 comma 1, such that f of x1 is equal to f of x2. So this implies us x1 over x1 plus 2, that is equal to x2 over x2 plus 2. So if we cross multiply these terms, we get x1 x2 plus 2 x1, that is equal to x1 x2 plus 2 x2. So this implies us x1 is equal to x2, and this gives us that the function is 1. The second thing that is given to us over here is that y is equal to range of f. It means this function is onto function. It means combining both these results, we obtain that this function is invertible. Now we have to find the inverse of this function. So to calculate the inverse, we are equating y, writing y is equal to x over x plus 2. So this implies us 1 by y is equal to x plus 2 over x. So this gives us that 1 by y is equal to 1 plus 2 by x. So 2 by x is equal to 1 by y minus 1, and this is equal to 1 minus y. So the value of x that we will obtain, or we are saying x by 2 we obtain, it is y over 1 minus y. So this gives us x is equal to 2y over 1 minus y. So this is the value of f inverse. Now the domain of this function f inverse, it is y, and the range of, or the codomain for this function, it is -1 to 1 closed interval, and this is the definition of the f inverse that we have. The next question we have is, let f is a function defined from n to y, where fx is equal to 4x square plus 12x plus 50. So the domain of this function, it is natural numbers, and y is equal to range of f. We have to show that f is invertible, and we have to find the value of f inverse. So to prove that f is invertible, we are writing, suppose x1 and x2, these are the natural numbers. So for f of x1 is equal to f of x2, this implies us 4 of x1 square plus 12x1 plus 15, that is equal to 4 of x2 square plus 12x2 plus 50. So this 15 gets cancelled, and we are left with this 4 times x1 square minus x2 square plus 12 times x1 minus x2 equal to 0. So this implies us x1 minus x2. If we take this 4 common, we are left with 3 over here, and if we take x1 minus x2 common, we are left with x1 plus x2 plus 3 is equal to 0. As both x1 and x2, these are the natural numbers, so we get that this term is always greater than 0. So this implies us that x1 minus x2 is equal to 0. So this implies us x1 is equal to x2. So this thing proves that the given function is 1 function. Next, it is already given in this question that the codomain of this function, this y we are talking about, this is equal to the range of the given function. So it means this function is an onto function, and as it is both 1 and onto, it means it is an invertible function. Now we have to find the inverse of this function. So we equate this 4x square plus 12x plus 15, we equate it equal to y. Now if we complete the square of this term, we obtain this is 2x plus 3 whole square plus 6. So we are going to complete the square. We are writing it is just like 2x square plus 12x. So this 12x we can write it is 2x should be there, then there should be a term, and it is 2 is already present over there. So the term present over here, it is 3. It means the term we have over here, it is 3 square. We add 3 square and we subtract 3 square from this term. So when we add 3 square, this whole term, this will become 2x plus 3 whole square, and this term we have, it is 15 minus 9 is equal to 6. So we obtain that y is equal to 2x plus 3 whole square plus 6. Now if we move the 6 on this side, we obtain y minus 6, that is equal to 2x plus 3 whole square. So this implies us 2x plus 3, that is equal to square root of y minus 6. Negative sign is not there because we know that this x is a x is a natural number. So 2x plus 3, this is a natural number, it should be positive. So we are saying it is equal to square root of y minus 6. So we obtain the value of x is equal to 1 by 2 times the square root of y minus 6 minus 3. So we are saying the function f, it is defined from y to n, and the definition of this function f inverse, it is given by f inverse is equal to 1 by 2 square root of y minus 6 minus 3. Next we have is let f be a function defined from R to R, and fx is equal to 10x plus 7. We have to find the function g from R to R such that g of f is equal to f of g is equal to R. So this is the definition of the inverse of the function. So we have to basically we have to prove that this function is invertible, and we have to find the inverse of this function. So to prove that this function is invertible, we are considering x1 comma x2, it belongs to R. We are saying f of x1 is equal to f of x2. This implies us 10x1 is equal to 10x1 plus 7. This is equal to 10x2 plus 7, and this implies us x1 is equal to x2. It means this function is 1 function. Now if we equate, we have to find the range of this function. So if we equate this to y, we are saying suppose y is the answer for all x, we substitute from R. We are saying y is equal to 10x plus 7. So this gives us x is equal to y minus 7 by 10. It means this x can take any values. We are saying that the value of x, it is R over there, and when we look at this function over here, we can say y belongs to R. It means the codomain that of the function f, we are talking about, this is the codomain of the function f, that is equal to the range of function f, and this range of function f, this is equal to the domain of the function if we write this function as g of y, then we are saying this is equal to domain of the function g, and this function, this gives us the inverse of the given function. So the inverse of the given function, we are saying that at f inverse, that is equal to y minus 7 over 10. Domain of this function is r, codomain is r, and this function y, f inverse of y, we are saying this is basically the function g that we have to calculate, g of y, that is equal to y minus 7 over 10, for which this definition of inverse will hold. Next we have is let A is equal to the set 1 to 3 and f is a function defined from A to A, and the definition of this function, it is given over here, that f is mapping 1 to 2, 2 to 3 and 3 to 1. Find f inverse if it exists. So if we look at this function over here, we are saying we have an element 1, 2, 3 in A, we have the elements 1, 2, 3 in A, and this function is defined from A to A, and this 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1. So clearly there is no element in the codomain whose pre-image does not exist, and secondly that every element of the codomain has a unique pre-image. So it means that this function f, it is both 1 1 and on 2, and this implies us that this function is invertible. Now we have to write the inverse of this function. So the inverse of this function f inverse, that will be defined from A to A, and it will map the elements. F inverse, we are saying it will be 2 comma 1, 3 comma 2 and 1 comma 3. Look at this, is the definition of f, and this is the definition of f inverse. The elements over here, they have changed their coordinates. Next is prove that an invertible function has a unique inverse. We have to prove that. We have already proved that an invertible function, it has an inverse. Now we have to prove that the inverse that exists, it is the unique inverse. So let us consider that there is a function f defined from A to B, and let g and h, they are the inverse of this function. It means g is defined from B to A such that FOG is equal to IB and GOF is equal to IA. We are saying there exists a function h from B to A which satisfies FOH is equal to IB and HOF that is equal to IA. Now we are saying this FOG is equal to IB because G is the inverse of the given function f, and FOH is equal to IB. We are talking about these two conditions. One is FOG is IB, second is FOH is IB. So what we get is that FOG of y, that is equal to FOH of y. Now this thing implies us that f of gy, that is equal to f of h y, and this thing holds for all y belongs to B. So this thing gives us g of y is equal to h of y for all y belongs to B, and this thing gives us g is equal to h, that is both these functions g and h, these are equal to each other. So what we have considered? We have considered that if possible, let there be two inverses g and h, and we have proved that if such a case is there, then g and h, they are equal. It means f has a unique inverse. Next is let f be an invertible function. Then we have to prove that f inverse of inverse is equal to f. So it is given that f is invertible. So it means f is 1 1 and onto. It is bijective function. So suppose we are saying there exists an element x belongs to A, and it is such that f of x is equal to y. A we are saying it is the domain of the function. F we are considering it is from A to B. So as this function is 1 1 onto, that is, it is invertible. So we are saying that x is equal to f inverse of y. Now f inverse of f of x, that is equal to f inverse of fx, that is equal to, what is f inverse of fx? That is equal to f inverse of y. Look at this value over here. We are talking about fx, and we know that fx is equal to y. So we are obtaining this term, and f inverse of y is equal to x. So what we get is that f inverse of f, that is equal to I A. Now if we consider the element y that belongs to B, then f being onto, there exists an element x belongs to A such that f of x is equal to y. We are considering the element y that is from the codomain, and as this function is both 1 1 and onto, it means this B is the codomain as well as the range of f. So as it is the range of f, so for every y belongs to B, there exists an x such that f of x is equal to y. Now if we calculate the value of f o f inverse of y, we are getting it is f of f inverse of y. This is equal to f of x, and this is equal to y, and this is equal to I B of y. So what we get is that f o f inverse, this is equal to I B. Now look at these conditions over here. We are saying f inverse of f, that is equal to IA, and f of f inverse is equal to I B. Now what is the definition? Suppose in place of f inverse I am writing it is G. In place of this f inverse I am writing it is G. So G O f is equal to IA, and f o g is equal to IB. So this thing means that f is inverse of G. What is G? G we have considered it is f inverse. So it means f is inverse of, in place of G, now we can write it as f inverse, and this is what we have to prove, that f inverse of inverse, that is equal to f. Now the next theorem we have is, let f be a function defined from A to B and g be a function defined from B to C, and it is given that both these functions, these are 1 1 and onto functions. Now we have to prove that the function g o f defined from A to C is 1 1 onto, and the value of g o f inverse, that is this function is invertible, and inverse of this function is equal to f inverse of g inverse. So we consider two elements x1 and x2, they belong to the set A. We are calculating the value of g of f of x1. We are saying suppose this is equal to g o f of x2. So this implies us that g of f of x1, that is equal to g of f of x2. Now it is being given that g is a 1 1 onto function, that is it is a 1 1 function. So it means that if we have g of x1 is equal to g of x2, it is basically this x1 and x2, now we are considering these are elements of B, then this thing should imply that x1 is equal to x2. So same thing is over here, that in place of this x1, now we have it as fx1, in place of this x2 we have fx2. So this answer will become, this is f of x1 is equal to f of x2. Now again this f is 1 1. So this thing implies us that x1 is equal to x2. So what we get is that GOF of x1 is equal to GOF of x2. This implies x1 is equal to x2. So what we get is that GOF is 1 1 function. Next we have to prove that this GOF is an onto function. So suppose we are considering an element C that belongs to the set. We are talking about this set GOF from A to C. So we are considering an element C which belongs to C. Then it is given that G is onto. It means there exists an element B belonging to B such that G of B is equal to C. Now this element B belongs to B. So if B belongs to B and it is given that F is onto, it means there exists an element A belongs to A such that F of A is equal to B. So if we substitute this value over here, we get that G of F of A is equal to C. This gives us GOF of A is equal to C. So we are saying that for every C belongs to C, there exists an element A in A such that GOF is equal to C. So this thing proves that the function, this GOF we are talking about, it is an onto function. We have proved that this function G, it is an onto function. So we have proved both the results, that GOF is 1 1, GOF is onto. It means GOF is invertible. Now we have to calculate the, now to calculate the inverse of this function, we are saying suppose there exists an element x in A such that f of x is equal to y, and there exists an element y in B such that g of y is equal to z. And as both the functions f and g are invertible, so this gives us x is equal to f inverse of y, and this gives us that y is equal to g inverse of z. Now from this what we get is that if we want to calculate the value of GOF of x, the answer we have, it is g of fx. This is equal to g of y, and that is equal to z. So this thing implies us that GOF inverse of z, that is equal to x. This result is mentioned over here, that GOF of x is equal to z implies GOF inverse of z is equal to x. Now if we calculate the value of f inverse of g inverse of z, the answer we obtain, this is equal to f inverse of g inverse of z. Now what is g inverse of z? G inverse of z we have already seen, it is equal to y. So this thing equal to f inverse of y. And what is f inverse of y? F inverse of y, the value we have, it is equal to x. So this is equal to x. So what we find from this is that GOF inverse of z is equal to x, and f inverse of g inverse of z is equal to x. It means both these values, these are equal. So this implies us that GOF inverse is equal to f inverse of g inverse. Now the next question we have is, let f be the function defined from R to R, and the function fx is e raised to power x minus e raised to power minus x. This function we are talking about, fx is equal to e raised to power x minus e raised to power minus x by 2. This function is basically sine hyperbolic x, and this function is an increasing function. You can see our video related to the hyperbolic functions. Over there you will find these kind of results. So we are saying this function, it is strictly increasing function. So it is 1 1. Next we are talking about the function. This function we have to prove that this is onto. So we are saying that this function, it is strictly increasing. It means it is monotonic function, and for monotonic function we know that the range of that function, it is given by f of minus infinity comma f of infinity. Why minus infinity and infinity? Because the domain of this function, it is given to be minus infinity to infinity, that is all real numbers. So when we substitute these values in this formula, we obtain that the range of this function, it is minus infinity to infinity, that is equal to r. So that is equal to the codomain of this given function. So what we get is that this function is both 1 1 and onto function, and hence it is invertible. Now to calculate the inverse of this function, we are equating it equal to y, and we get it is equal to e raised to power x minus e raised to power minus x by 2. This is equal to e raised to power 2x minus 1 by 2 e raised to the power x. This gives us e raised to the power 2x minus 2 e raised to the power xy minus 1 is equal to 0. So this implies us e raised to power x is equal to 2y plus minus square root of 4y square plus 1 over 2. So this implies us that x is equal to log of y plus minus square root of y square plus 1. So the value of f inverse of y we have, that is equal to log of y plus minus square root of y square plus 1. Now if we consider the value of e raised to the power, this value we are talking about, if we are considering the value of e raised to the power f inverse of y, we are saying the answer we will have it is y plus minus square root of y square plus 1. Now look at this number, it is e raised to the power something, this is always positive, it means this number cannot be negative. So what we obtain is that the negative sign over here, it is not possible. So the final answer that we will obtain, it is f inverse of x is equal to log of x plus square root of x square plus 1. This is the inverse function of the given function. Now in this next question, we are given that f is a function defined from closed interval 1 by 2 to infinity to closed interval 3 by 4 to infinity. We have to, this function is defined like fx is equal to x square minus x plus 1. Now on this domain and for this codomain, this function, it is both 1 1 and onto. Now we have to find the inverse of this function. So when we look at this function, it is fx is equal to x square minus x plus 1, and we can write this is equal to x minus 1 by 2 square plus 3 by 4. So from this we can see that the value of this function, the answers we will obtain, it is always greater than equal to 3 by 4. So we are saying that the codomain and range, they are equal, and it can attain any value. This function, it is defined for all values of r, but over here this domain is given to us. So for this domain also, we are saying that this function is onto function. Further, to prove that it is 1 1, we can consider the elements in the form x1 and x2 that belong to the interval 1 by 2 to infinity, and we are writing f of x1 is equal to f of x2. This thing implies us x1 minus 1 by 2 square plus 3 by 4, that is equal to x2 minus 1 by 2 square plus 3 by 4. This 3 by 4 gets cancelled, and we are left with this x1 minus 1 by 2, that is equal to x2 minus 1 by 2 square. So this thing implies us x1 minus 1 by 2 is equal to x2 minus 1 by 2, or x1 minus 1 by 2, this is equal to minus of x2 minus 1 by 2, and this thing gives us, this 1 by 2 gets cancelled, that x1 is equal to x2, or x1 is equal to minus of x2. Now we are saying that the values of x1 we have, x and x2 we have, x1 and x2 we have, they are positive. It means this case is not possible. So what we obtain is that x1 is equal to x2. So we are saying that this function is both 1 1 and onto. So it means it is an invertible function. Now to calculate the value of the inverse, we are saying equate y is equal to x plus x minus 1 by 2 square plus 3 by 4. So this thing gives us the value of x we obtain, it is equal to, on solving this we will obtain the value of x is equal to 1 by 2 plus minus square root of y minus 3 by 4. We are saying the value of x can never be negative. It means that we are ignoring this negative sign over here. So the value of f inverse we have, it is equal to f inverse of y is equal to 1 by 2 times 1 by 2 plus square root of y minus 3 by 4. So we are saying this function f inverse of x is equal to 1 by 2 plus square root of x minus 3 by 4. Now the next part of this question is we have to solve the equation. It is x square minus x plus 1 is equal to 1 by 2 plus square root of this term. Now look at this term over here. This term, it is coming from over here, it is f inverse of x, and this term we are saying x square minus x plus 1. This is the given function. So we are saying what we are given over here is that fx is equal to f inverse of x. Now we know that if we draw the graph of both these functions, we are talking about one function we have, it is y is equal to fx, and second we have y is equal to f inverse of x. Suppose this is the graph of the function y is equal to fx, then the graph, this is y is equal to fx, then the graph of the function y is equal to f inverse x is the mirror image of this graph along the line y is equal to x. It means the solution of this equation, they are same as the solution for the value of fx is equal to x, and this thing is mentioned over here, that the solution of f inverse of x is equal to fx and the solutions of fx is equal to x, they are same. So we are writing this equation in the form that fx is equal to x implies x square minus x plus 1 is equal to x, and on solving this we obtain that x is equal to 1 is the required solution. Now the next question we have is, if function f and g are defined as fx is equal to e raised to the power x and gx is equal to 3x minus 2, where f and g, these are defined from R to R, find the function GOF and FOG. Also find domain of FOG inverse and GOF inverse. Now these functions, these are given to us. We want to find the FOG of x. So that will be equal to f of g of x. So that will be equal to, we are writing it is f of 3x minus 2, and this is equal to e raised to the power 3x minus 2. Next we have to write the value of GOF of x. So that is equal to g of fx, and this is equal to g of, what is fx, it is e raised to power x. So it is equal to 3 e raised to the power x minus 2. Now these are the two functions we have calculated. Now we have to find FOG inverse and GOF inverse. So we are saying FOG of x is equal to y. So this thing implies us that e raised to power 3x minus 2 is equal to y. So this gives us 3x minus 2 is equal to log y. So this implies us x is equal to log y plus 2 upon 3. So what we get from this is that FOG inverse of y, that is equal to log of y plus 2 by 3. So the domain of this function will be, for this function will be defined for y is greater than 0. So it means the domain of this function will be 0 comma infinity. Next we have to calculate the value of GOF of inverse. So we are equating this equal to y. So this implies us x is equal to GOF inverse of y. Now if we substitute the values over here, what we get is x, what is GOF of x? GOF of x we have calculated, that is equal to 3 e raised to power x minus 2. So we get that 3 e raised to the power x minus 2, this is equal to y. So this implies us e raised to the power x is equal to y plus 2 by 3. So this gives us x is equal to log of y plus 2 by 3. So the domain of this function that we have over here, the domain of this function will be y plus 2 by 3 should be greater than 0. It means y is greater than minus 2. So the domain we have, it is minus 2 comma infinity. So we have obtained that the domain of the function GOF of inverse, that is equal to minus 2 comma infinity, and the domain of the function FOG of inverse, that is equal to 0 comma infinity.